Now, conservation of mechanical energy only holds for frictionless systems with no external force. Okay. So if you want true conservation, you have to account for all the energies in the universe. Right. So in particular, basically, the amount of energy in minus energy out the system is basically the change in energy of the system. And this right here is due to external work. Right? This could be something like your arm pushing or something or whatnot. Okay? Alright, so let's consider example, a ball that bounces to rest, right? So if you put a ball, you start bouncing it and leave it bounce, eventually it will stop bouncing, right? So let's consider a 0.1 kilogram ball falling 2 meters and eventually coming to rest. Right. So in this case, basically, the change in energy of the system, well, there's going to be several things. First, it's going to equal to the change in mechanical energy plus the ball is bouncing up and down. It basically has to convert that mechanical energy to some other form. That other form is going to be heat, so change in the thermal energy. Okay, it could be other system energy as well. It could be nuclear energy, chemical energy, whatnot. But for the most part, we don't care about that. Okay. Now this is going to be equal to 0. There's no external thing acting on this thing, so it can be 0. Is equal to change in mechanical energy. It's going to fall 2 meters, so it's going to be mg delta h, right? The change in the height of the ball, plus the change in the thermal energy, right? So it's going to be basically mg times 2, right? Plus change in thermal energy, right? And so what you get is that the change in thermal energy, it's 0 minus 2. Change in thermal energy is equal to 2 mg, right, the 2 meters, which is equal to 2 times 0.1 times 9.8. That's 1.96 joules, right? Okay. So let's try a different example. Here's another example here. So let's consider the energy dissipated by kinetic friction. I have an object here, weighs about 10 kilograms. It's sliding along a surface with mu of k equals 0.5 and slides some distance delta x, right? Right, the velocity of this thing might be 5 meters per second to start, for instance, right? Okay, so change the energy of the system is equal to change in the mechanical energy plus change in the thermal energy. Okay, so we can basically try to compute out what the energy, what the work done by friction would be. All right, so let's first compute. Work done by friction. Right? So work done by friction, if I do this correctly, is equal to the integral of f sub f dx, right? Let's look at this plot here. Let's basically say x is in this direction. So this is just going to be F, force of friction is this way, F of F. So it's going to be minus mu k mg, right, because it's kinetic friction, that's always value. The minus sign comes from the direction of this thing, right, times basically integral of dx. So it's basically minus mu of k mg delta x, right? That's this little slide, okay? So this work goes into thermal energy, right? So in fact, the change in E thermal is equal to V minus the work done by friction, which is equal to then mu k mg delta x, right? So just switches the sign, right? And so the change in the mechanical energy is equal to the work done by friction. This is minus mu k mg delta x, right? So wherever it goes, leaves one thing has to go in the other one, right? Now let's basically take a specialized case for delta x equal to 1, so 1 meter, say, for instance, right? Then the change in the thermal energy is equal to minus Wf is 0.5. What was that? It was 10. G was 9.8. Delta x is 1. This is 49 joules, right? And the change in the kinetic energy, that's basically Wf, sorry, right, be minus 0.5, 10, 9.8, 1, that's going to be minus 49 joules, right? Now, can this happen forever? Can this thing continuously lose energy? No, the answer is no, right? The total kinetic energy, the mechanical energy, is equal to 1/2 mv squared. That's 1/2 times 10 times 5 squared. It's 125 joules, right? So the maximum energy I could lose is based on 125 until it comes to rest. So basically, delta E mechanical max is basically 0 minus E mechanical, which is minus 125 joules, right? So I can't go higher than this, basically, right? I basically lose all my velocity, and that's it. I'm done, right? Okay. Now we can estimate how far that would take us. So that basically implies that we set this equal to Wf, right? So this is equal to mu k mg delta x. Now I don't have to assume anything about delta x anymore, just find what that is. That's 0.5 times 10 times, let's see what I say here, 9.8, right? Delta x maximum, we'll call it maximum, right? This will imply delta x maximum is equal to 2.5 meters or so. All right, so that's basically how far it was flying. Okay. All right, so that's basically one. All right. Let's look at another one. All right. So here's another example of this. Let's go down a slide or plane. Imagine I have an object here. It sits up here with a mass of 10 kilograms. It slides down this thing, right? Let's say it slides 10 meters or so, right? All the way down to the bottom, right? And this angle here is 30 degrees, say, right? Okay. And let me give this a friction. This is 0.5 to make it simple. And I'm going to make G equals 10 meters per second squared, right? Because I don't want to deal with 9.8 anymore, to tell you the truth. Okay, so let's take a look at this thing, right? So, delta E system is equal to delta E mechanical plus delta E thermal, right? Okay, let's go see what the amount of work done by friction is, right? So delta E mechanical is equal to work done by friction, which is equal to mu k f of n with a minus sign dx, right? This points this way. This is f of f. Let's basically choose the x-axis along this positive direction here. All right, so f of n in this case is mg cosine theta, right? So delta E mechanical is equal to, let's take a look, this is mu k mg cosine theta integral dx minus sign minus mu k mg cosine theta delta x, which this way in that case will be 10, right? So let's look at this thing. So it's going to be equal to 0.5 minus sign. That's 10 kilogram. That's 10 again for G. Cosine 0 is 0.866. So what's that? 43.3 minus sign. Okay. Wait. Delta x, right? Delta x. So over delta x equals 10 meters. That implies it's 400, delta E mechanical is equal to minus 433 joules, right? Okay, so what is V at the end? So the mechanical energy, this is V equals 0, so it's at rest. Mechanical energy at 1, 2, is equal to 1/2 mv squared plus mgy, okay? Let's pick y equals 0 here, and let's pick y pointing up, all right? So this is equal to 0 plus mgl, or mg delta x sine theta, right? So this is going to be 10 times 10 times 10, sine theta is 0.5. That's 500 joules, say for instance, right? So E mechanical at 0.2 is equal to 1/2 mv squared plus mgy. That's 1/2 mv squared. That's basically some velocity at the very end. Plus now this could be y equals 0, mg times 0. That's 1/2 mv squared is equal to 500 joules. All right. So you can go ahead. Wait, hold on. sorry, not 500 joules. I apologize for that. It's basically something, all right? And so what we have is the mechanical energy at 2 is equal to, well, let's write it like this. Mechanical delta E mechanical is equal to E mechanical at 2 minus E mechanical at 1, if I know the relative to two things, which is equal to WF, which is equal to minus 433 joules, right? So let's figure this out. So this can be equal to, we determined the mechanical energy at 2 is 1/2 mv squared minus 500 joules, I just determined that, is equal to minus 433 joules. And so, what this says is that 1/2 times 10, v squared is equal to 67, which I believe is, let me just calculate that out, let's make sure. Okay, let's go get that calculator out. Oh, a great calculator for this. 67 divided by 5, 13.4. V is equal to about 3.6 meters per second. Okay, pretty simple. Okay, last but not least, let's go after one more example here. Let's imagine I have a spring here. Okay. And it's been compressed. So this thing has been compressed from the equilibrium position. X is equal to, well, by 1 meter. So this is X equals minus 1. X equals 0, and I'm going to let this thing spring back until it gets to this point here, right? Now, the thing is I'm putting on some surface here, which has some coefficient of kinetic friction equal to 0.5, is that right? No, 0.25, which was that instead. Right? And I want to basically see what's the velocity v at that point, all right? So let's go ahead and figure out what the mechanical energy is. So this is basically situation 1, situation 2, right? So the mechanical energy at 1 is 1/2 mv squared plus 1/2 kx squared. Let's put k is equal to 100 newtons per meter, right? So it's going to be equal to, well, this is 0, the first part is 0, plus 1/2, k is 100, x is 1 squared, so that's going to be equal to 50 joules, right? Now, let's look at the change in mechanical energy, which is the work done by friction, which is equal to integral of mu of k mg with minus sign dx. This is basically minus mu of k mg. Delta x is 1 in this case. So it's going to be equal to, let's see, so mu k is 0.25. What did I choose mass? This thing to be 10 kilograms. Okay. The mass is 10 kilograms, g is 10 as well, and x is 1. Okay, delta x is 1, minus sign. So it's equal to minus 25 joules, right? So, what that means is that energy, mechanical energy at 2 is equal to mechanical energy at 1 plus delta E mechanical, which is 50 minus 25 is 25 joules. And mechanical energy at 2 is just basically 1/2 and v squared plus 1/2 kx, where x in this case is 0. Okay. So it's going to be equal to let's get this right. It's 5 v squared is equal to 25. So v squared is equal to 5. And that's about 2.3 or so. Let me just check that real quick. Square root of 5. 2.2. Okay. All right. And so that is it for basically conservation of energy when you include frictional terms.